Bismillah ar-Rahman ar-Rahim. So last time we talked about automatic summarization for rep version 1, and we said that the limitation for rep version 1 not sending the subnet mask as part of the route update initiated or forced the rule for automatic summarization that if the route entry is coming on an interface that exists on the same major network of the destination address of this route entry, then we use the subnet mask of that interface and assign it to the route entry in the routing table. Otherwise, if the destination address in the route entry is incoming on an interface that does not exist on the same major network, then we use the classful subnet mask and assign it to the incoming route entry. And we said that one of the disadvantages of automatic summarization is what we call the lack of support for discontiguous networks. And by that we mean that if you have this contiguous network, so if we take a look at this scenario here, we notice one thing very important, that you have a network that exists in a network address 172.30.1.0 or .2.0. So this exists in the major network of 172.30.0.0/16. And also you have part of the same major network on the other side. Between them there is there are some networks that exist on different major networks. So using the terminology that we discussed before, R1 is considered a boundary router to these two networks, and R3 is also considered a boundary router, but it happens that those two sides exist on the same major network, and there is one network between them. That's what we call discontiguous networks. That you have part of the network here, part of the network there, and between them there is another major network. So the problem here is serious, because a problem like this, this discontiguous network scenario, may in fact cause, and in that case it will in fact cause rep version 1 not to converge, and it will cause some mistakes and wrong routing. Let's see how that happens. Using the automatic summarization rule, when R1 sends route update about any of these two networks, okay, from R1 to R2, R2 has a route entry that says 172.30.1.0 or 172.30.2.0, right? Those two updates are coming on an interface that exists on a different major network, right? So those two route updates will be summarized at R2, right, as a 172.30.0.0/A16, because it's coming on an interface that exists on a different major network. That's what we discussed last time, right? So R2 will summarize this to 172.30.0.0. So I have a route entry that says if you have any destination that goes to 172.30.0.0, send it through R1. Okay? Type. After that, R3 will send route updates about 200.0 and 100.0. And guess what? They are coming on an interface that exists on a different major network. What does R2 do in that case? It will generate a route entry in the routing table that says those two updates are coming on a different major network, than this interface. So it will summarize them and it will generate a route entry that says 172.30.0.0, okay, goes to R3. So in that case, you have two route entries. Both of them, they have the destination address 172.30.0.0. One that says go through R1, and another one that says go to R3. Go through R3, right? And both of them, they have the same hop count, right? Both of them will have the same hop count, which is in that case 1. So the hop count will be 1, right? Because R1 is directly connected to these networks, so when it sends here, it will send with a hop count of 1. R3 will send here with a hop count of 1, right? So you have two routes with a hop count of 1, okay, going to the same destination address. What does R2 do in that case? You have two incoming routes and the route updates with the same cost going to two different directions. What are we supposed to do? No one remembers? Load balancing, bravo عليك. Load balancing. So if I have two incoming route entries with the same cost or with the same hop count, then I cannot accept one over the other. So I will put them both and I will do load balancing. Okay? Is that correct? Is that the correct behavior? So this way, if I have a destination, if I have a packet sent from here through R2, okay, with a destination address of 172.30.100.0, will it always go here? No, load balancing will send it here or here. It doesn't matter. For load balancing, it doesn't matter. It may send it here or here. Okay? One time it will send it here, one time it will send it here. Which is not correct, right? So this simple scenario caused the routing to not to work correctly. So these contiguous networks with automatic summarization may in fact cause serious problems. It's not that it will not work efficiently. It may not work at all. It may cause no conversions using RIP version 1. That's one of the biggest limitations, and that's why we highlighted last time that the network administrator needs to be very careful when he or she designs the addressing of these subnets. You need to have no discontiguous networks, because that scenario is really serious and it may cause some routing errors. Okay? This is not routing loops. So this is different from routing loops. This will cause load balancing in an incorrect way, because you are doing some summarization where you should not do that. But REP has to apply this rule because of the limitation that it cannot send the subnet mask as part of the route updates. And that was one of the motivations for RIP version 2. So RIP version 2 eliminated this limitation completely by supporting the subnet mask as part of the route update. And that's why RIP version 2 is actually a classless routing protocol. Okay, so that's one of the immediate updates in RIP version 2. Any questions? So that's the summarization. Unfortunately, we will not have time to talk about RIP version 2, or we're going to have to skip some of the topics in RIP version 1 as well, like default route and these kind of topics. So we'll jump directly to EIGRP, because these are very important routing protocols that we need to learn about. So EIGRP started with the baseline protocol, which is IGRP. An IGRP was developed in the 90s, in 1980s, sorry, in 80s, to overcome the limitations of RIP. So when RIP version 1 came about, and it had some limitations, so some people took the direction of enhancing RIP version 1 to have RIP version 2. And Cisco, on the other side, they actually took another direction to develop a new protocol altogether using their proprietary protocol of IGRP. IGRP was supposed to overcome two limitations. One is the concept of classful routing protocol. So definitely IGRP is classless routing protocol. So it deals with subnet mask as part of the route updates. The other thing is the metric. The fact that we use hop count is really limited because the internet is by nature heterogeneous. So you have different types of networks and different types of links. So you have fiber optics, and you have UTP and STP, and you have 10 base T Ethernets. You have 1 gigabit Ethernet. We have 10 gigabit Ethernet. We have wireless. We have 3G. We have 4G. So in general, you have heterogeneous network. So it doesn't make any sense that all the lengths would have the same weight, because in nature they don't. It doesn't make any sense to balance or to consider a wireless link equivalent to a 10 gigabit Ethernet link, because it's not logical. So instead, IGRP used a composite metric. So the concept of composite metric is based on the fact that you use multiple parameters of the link, okay, and combine that into one metric. And as we talked about before, IGRP uses 4 different parameters: bandwidth and delay, and those are offline parameters. What does that mean? This means that the bandwidth is a parameter, and it's based on the type of the link, but it does not change in real time. Okay? So these two parameters are not supposed to change in real time. Okay? So depending on the type of the link, if you have, like, for example, 10 gigabit Ethernet, then this bandwidth will be 10 gigabit Ethernet. That's it. It does not change over time. The delay is also based on the type of the network. If you have Ethernet, for example, it's 100 microsecond. If you have serial WAN link, then it's 100 millisecond, and so on. So it's supposed to be fixed. Those two are supposed to change in real time. So reliability and load, especially the load, we can understand that the load changes over time. So depending on how many connections are going over a link, this load may change. This link, for example, is loaded مثلا 50%. This link is loaded 80%. And it does affect the routing behavior, of course, because if I go through the North Road and I know that there are some traffic jams, even though it's the shortest path, it may be the shortest path or the fastest, but it doesn't make any sense that I go there and I know that there are some traffic jams, right? So IGRP tries to resolve that by incorporating load and reliability. And also reliability talks about the probability of failure. So if you have a link and over time it fails multiple times, then this probability goes high. The probability of failure goes high, which forces the cost to go high. Okay? So you go into a street or a road, and the possibility of having this road, of having some obstacles or some construction in this road is really increasing. Okay? So again, this is an indication to you that you should not go through that, because the cost is going to be high. Okay? So these metrics or these composite these parameters, they are jointly or combined into one composite matrix. We'll see how we calculate that. So the format of the EIGRP is obviously significantly more complicated. Of course, something you notice here is that, again, we skipped IGRP and we'll start talking about EIGRP directly. EIGRP is just an evolution of IGRP, enhanced IGRP, okay? It's equivalent to REP version 2, okay? So EIGRP has a message format which is obviously more complicated, significantly more complicated than REP version 1. In REP version 1, we talked about a header and we talked about a payload that contains, again, it contains nothing but the next hop and the hop count. That's it. And you have 25 of these in one message. So if you have more routing entries, then you need to divide these between multiple route updates using the rep message format. Here, as we will see, we have also a data link layer, header, and we have IP. And then after that, we have EIGRP packet header. There's something missing here. Does anyone remember where, in REP version 1, what's missing here? If you need to send any message, you need to have a transport layer protocol. So you don't have any transport layer header to send the route messages using EIGRP. So that's something strange. EIGRP does not use TCP or UDP. Why? Well, it turns out that EIGRP, when it was designed originally, it was not designed solely for IP. It was designed for IP, for IPX, for AppleTalk, for different types of routing protocols, or network layer protocols. So EIGRP was designed for different network layer protocols, not just IP. So in fact, this IP header may be replaced by IPX header or AppleTalk header. Okay? So, but what about the transport layer header? Doesn't IPX or AppleTalk have some kind of a transport layer protocol? Well, it's not. It doesn't have to necessarily be a specific transport layer protocol. And that's why when Cisco designed EIGRP, they decided to have their own transport layer protocol as part of the EIGRP. Unlike REP, if you remember, REP used to use what? UDP. So REP uses UDP over IP, fixed. And REP uses or works only with TCP IP. Okay? And instead, here, EIGRP can work with different network layer protocols. So that's one major difference in the case of EIGRP. And you will notice that the header here has a lot more fields than just the version and the fields that REP used to use. Okay? This is the payload, and here in the payload, again, REP used to use only one message format with command, request or reply, and we talked about that. And then the route entries are concatenated into like 25 different route entries. Okay, each route entry would contain only the next hop and the hop count, or the cost, or the distance. Okay? We will see here that we have different message formats to indicate different things. So EIGRP is by far much more complicated than. So let's dig in and see how the packet header and the payload are designed. So first, the packet header contains the opcode or operation code field. So that simply corresponds to the command field in RIP. However, this opcode can have 4 different values. Unlike the command in RIP, the command used to have a 1 or 2, right? Request or reply. Okay. Here, it can have 1, 2, 3, or 4. 4 different types, which we will talk about. Okay. As we can notice here, one thing we have to observe is these 3 fields: flags and sequence and acknowledgement, which did not exist in RIP. And if we remember TCP and how it's designed, we can really associate these fields to some fields in TCP, which really indicates that EIGRP has a built-in transport layer protocol, which is somewhat similar to TCP. Okay, and in fact, it's true. It has some overlap with TCP, but it can work in a reliable way or unreliable way. So TCP is reliable, which means that if I send a packet and it does not get on the other side, I will keep sending it forever, right? That's TCP. Here, no, you can send it using reliable or unreliable. Okay, so this in fact can work as TCP in some condition and can work as UDP in some other condition. Okay, we'll talk about that. So we have operation code, which is 1, 2, 3, 4, and we have a transport layer protocol. It's called Reliable Transport Protocol, RTP. Checksum, of course, for error correction and stuff. And you have another field, which again, it did not exist in RIP, which is called autonomous system. So we know what autonomous system is. Autonomous system is grouping of group of routers to be supported or to be under the same authority. That's the definition of an autonomous system. However, the autonomous system inside the EIGRP message format indicates a slightly different thing. This actually indicates a process ID. So when you start EIGRP on a router, you have to give it a process ID. And a process ID is just an identifier of the EIGRP message that starts on the router. Because you can start multiple instances of EIGRP protocol on the same router. Okay? So when you start each one, you have to give it an ID. And guess what? In order for a group of routers to exchange EIGRP messages, they have to have the same process ID in order to exchange messages, which in a way can work as an autonomous system. So group of routers that have the same process ID or autonomous system, they can exchange routing entries together. But theoretically, you can have 2 or 3 of these process IDs in the same autonomous system. So the autonomous system field here is slightly different from the definition of an autonomous system that we talked about before. Here, autonomous system indicates a process ID. Okay, so the autonomous system field here indicates a process ID. So, so that's the packet header. So that's the packet header, and then you have the message payload, which is called type length values, TLV. They call it TLV, and these TLVs can have multiple message formats depending on what you need to communicate. One message format could contain the routing matrix parameters. These parameters are used in the calculation of the composite metric that we talked about. What happens here is that the routing metric the routing matrix, so EIGRP matrix equals K1 times the bandwidth plus K2 times I think load plus K3 times delay plus K5 times reliability divided by or times K4. So both K4 and K5, they are combined for the reliability. So K1 and K2 and K3 and K4 and K5 define the weight or the contribution of each of these parameters in the calculation of the composite matrix. By default, this is complicated, but by default, K1 and K3 are 1 by default, and the rest are 0, which really comes down to the fact that the metric is basically bandwidth plus delay. That's the default configuration of any EIGRP router. Very simple. So the default parameters here are K1 equal 1, K3 equal 1, and the rest of Ks are 0. Very simple. Okay? Okay. But this message has a little bit more than this. As we can see, we have, including K1, K2, K3, K4, K5, we have the hold time. And remember that hold time here is different from the hold down timer that we used to use in RIP. Okay? Things are starting to get a little bit close to each other, so pay attention to these differences. So autonomous system is not exactly the autonomous system that we talked about. Autonomous system field here indicates the process ID. Also, hold time here is different from the hold down timer that we talked about earlier. Okay? Hold time here, actually hold down timer is still valid for all distant vector routing protocols. But here, hold down time here indicates that, remember we said that EIGRP does not use periodic updates, right? It uses what? Triggered updates or event-based updates, okay? So in order for me not to send periodic updates, I have to feel any change that happens, okay? So there is still, when you say it's triggered updates, in a way we lied. So there is something underneath that still uses some periodic updates, but it's not used for exchanging routing information. Okay, this is called a hello protocol. Hello protocol is not used to exchange routing information. Remember that. Hello protocol is used only to indicate that I'm alive. I'm alive and well. So each router, okay, should send hello to all the neighboring routers to let them know that I'm alive. I'm alive. Okay, and this hello message should be sent, I think, in a frequency using time intervals of 5 seconds. So every 5 seconds, a router should say, I'm here, I'm alive. Otherwise, after some time, the neighboring routers will consider this router as a disconnected or down. And down here will trigger an update to all the neighboring routers using the triggered updates. But so underneath there is a hello protocol that's used to indicate whether there is some changes in the network or not. Okay. Type. Again, we didn't talk about hold time. Well, hold time is the time that a router has to wait before it considers another router down. And it's usually 3 times the hello frequency, which means that if the frequency of the hello message is 5 seconds, so a router should wait for about 15 seconds before it considers another router down, which means if I wait for 15 seconds and I did not receive any hello message from a specific router, then I have to go into the routing table and consider this router down, and in that case I should trigger a route update to send to all the other routers that router X is down, router X is down. Okay? So that's what hold time is. So hold time is used to for any router to wait for a specific duration. After that duration, you consider a router down. So if the router sends you a hello message within the 15 seconds, then you reset and you have to wait for another 15 seconds. And if you don't receive any message or any hello from a specific router for the entire duration of 15 seconds, then you consider this router down. Okay? So this is the first TLV type. So we call them TLVs. This is the message payload for EIGRP. In fact, there are some other types of TLVs which we will talk about. Any question? Okay. Another TLV which is called IP internal, and we have IP external. This IP external is not, in fact, used a lot because this is used for exterior routing protocols. If you remember, border gateway protocol, when we talked about the classification, the taxonomy of the different routing protocols, we talked about interior routing protocols and exterior routing protocols. We said that exterior routing protocols are used within different autonomous systems. It provides the inter-autonomous system routing. And one example for that is border gateway protocol. Okay? Well, it happens that EIGRP implements inside it another type of TLV which supports exterior routing protocols, or it's called IP external. And in here, as we can see, there are some fields that indicate originating autonomous system number. Here, the autonomous system number is the exact autonomous system number that we talked about before. So you have the originating router, originating autonomous system number, and then external protocol metric. And this is an external metric which is between two autonomous systems. So you deal with an autonomous system as an abstract notion of one router. It's as if one autonomous system becomes now one router, and another autonomous system is another router. And now you need to route between these autonomous systems using metric. Okay, so so you have, this is one autonomous system. This is one autonomous system, and this is one autonomous system. Each one of these is group of routers, okay? And these are connected like this. And then exterior routing protocol, it talks about external routing between these autonomous systems. So if I need to go from here to here, should I go this way or this way? Similar to, it's as if one autonomous system becomes like as a router, okay? But then you have to include different extra fields as originating autonomous system number and external metric and stuff like that. In any case, we'll not talk about this a lot. So the the IP internal TLV is more important in that case, because that's where you need to communicate the route updates using EIGRP. Okay, so here in this TLV IP internal, we use the hop count, and then we use the different parameters or the different values that we use to calculate the metric. Remember, in RIP, this actually contained simply the next hop and a hop count. Okay? Here, of course, we have a lot more than that. We have delay, we have bandwidth, we have load, we have reliability. And we have some other fields, including حتى الhop count if needed, but these are not in fact used. So if you need to go to this destination, your next hop is this, and these are the values that you can use to calculate the composite metric. Okay, so that's what this means. And similar to RIP, here you can group multiple TLVs in one message payload to communicate multiple route updates. Okay, so this can be repeated inside one message. Okay, each one of these has the hop count and the destination, because any route entry it says if you need to go to this destination address, you need to go to this next hop. Okay, you need to go this way, and your cost or your metric can be calculated using this value. Okay, so this value in that case is composite, and it contains the delay, bandwidth, reliability, and load. Of course, if we use the default configuration, we don't even have to use reliability and load, right? Because we only have K1 and K3 equal 1s, which means that we only care about delay and bandwidth, and that's why they are contained in the second and third field here. So you don't have to check any of these values in default configuration. Okay, so you only have to use those two values. Any questions? So we have 3 TLVs in that case. We have the EIGRP parameters, which is K1, K2, K3, all the way to K5, and the whole time. And the default configuration, K1 equal 1, K3 equal 1, and the rest equals 0. And you have whole time, which is by default 15 seconds. And you have TLV that indicates IP internal, and this contains the routing, the route information, and the external one, which contains, including the route information, you include also the autonomous system information to facilitate the exterior routing between the different autonomous systems. As we said, EIGRP uses its own transport layer protocol, which is called Reliable Transport Protocol. Reliable Transport Protocol here is used. It replaces TCP and UDP, so there is no support for TCP or UDP here. And the main reason for this is the fact that, as we said, EIGRP was designed to support all these protocols, not only IP. Okay, so it can be used for IP or IPX or AppleTalk or any other network layer protocol. The characteristics of RTP, or the Reliable Transport Protocol, is that it can be used either as a reliable transport or unreliable transport. The difference between the two is very simple. If you want to have unreliable transport, similar to UDP, then you send a message, you don't have to wait for acknowledgement. So you send a message, and if it does not arrive on the other side, that's fine, because it's unreliable in nature. Right? So that's what unreliable means. If you want to support reliable transport, then what you need to do is that for each message you send, you have to wait for acknowledgement. And if the message was not acknowledged, then you have to retransmit. That's what reliable means, right? So RTP can have both modes. It can work both ways. Okay, and we will see what types of messages that EIGRP uses reliable versus unreliable mode. We'll talk about that now. Not only that, the IGRP can use the RTP protocol to send messages either unicast or multicast. As we said, route updates can be sent as one hub broadcast to all the neighboring routers. But we talked about the fact that EIGRP uses triggered updates, partial updates, and bounded updates, right? We talked about these three characteristics for the route updates for EIGRP. Those are very important. The bounded updates talks about the fact that when EIGRP sends the routing information, it sends it only to the routers that are concerned with this change. Okay? So this means that you don't necessarily have to broadcast to all the routers around you. You can send to a subset of these routers. So in terms of communication, so you can communicate to the neighboring routers using unicast, which means what? You send to this router, and then you send to this router, and then you send to this router, and so on. So you send to each router with the specific IP address of that port, okay? Or you can use multicast, which means that you send one message to a group of routers, the same message to a group of routers in one shot, okay? Which is a little bit different from broadcast. Broadcast sends to an address which is all ones, right? The message, if the message has a destination address of all ones, this means that it goes out through all the ports, and it goes to all the neighboring routers. Multicast is slightly different. It uses an IP address in class D, if you remember the old days of 455, and multicast IP address can be used to send to a group of routers. Not a single router and not all routers. A group of routers which is a subset of all the neighboring routers. So that's how you indicate the IP address in the case of multicast. So in the case of multicast, you use an IP address which is 224.0.0.10. That's one example of a multicast IP address. That's in fact the one that's used for EIGRP to indicate multicast, okay? Any questions? So these are the characteristics of RTP. So it can work unreliable or reliable, and it can use unicast or multicast. We talked about the EIGRP message header, right? And in there we talked about the field opcode or operation code. And we said that there are 4 different types of messages that EIGRP uses, right? So operation code can be 1, 2, 3, or 4. So the first message type using operation code 1 is which is used for hello messages. And again, hello messages, as we said, because EIGRP uses non-periodic updates or triggered updates, we need to have another periodic means to indicate whether there is a change in the network or not, right? So for example, how can I feel that this router is down? Well, RIP did not have to do that because RIP by default uses a periodic updates. So in a way, periodic updates can be used as hello messages, right? But here we don't have periodic updates, so we have to use hello protocol to discover all the neighbors and discover whether these neighbors are alive or dead or down, right? So it happens that these hello messages, they go from one router as using multicast to all the neighboring routers, so it's broadcast, and it's unreliable. So hello messages, each router will send to all the neighboring routers hello message every 5 seconds, and hello messages is nothing but just EIGRP header to indicate hello. That's it. It does not have any TLV or message payload. It does not have any routing information. It doesn't have anything. Just indicating to the neighboring routers, I'm alive. That's it. And that's why it's unreliable. So when I send a hello message, I will not wait for acknowledgement. Okay? So the reliable transport protocol in that case will not expect any acknowledgement. So that's the first type of of messages. So the hello protocol is used to discover neighbors and form adjacencies. يعني this router will have to form its own neighbors. When it receives a hello message from here, it knows that it has a neighboring router that's called مثلا R1 and another neighbor which is called R2. And guess what? One thing to pay attention to here is that if these routers, they are physically connected to each other, right? Using these links. But when I start EIGRP, I have to assign a process ID to each of these routers, to the EIGRP process on each router, right? I have to assign the same process ID on all these three routers in order for them to become adjacent to each other. So if a router starts with a process ID and the process ID here is equal to here, only then this router will feel that it has some neighbors that are represented by these two routers. If under any reason I start EIGRP with a process ID 1 and I start here process ID 2 and I start here process ID 1, all of a sudden this router will have this as a neighbor, and this router will become a different router. It's an alien router. I don't know it. Okay, even though I'm physically connected to it, but logically EIGRP does not feel that it's a neighbor because it has a different autonomous number or it has a different process ID. Okay. So in order for hello messages to be exchanged between the routers, they have to have the same process ID. If they all have the same process ID, then they will exchange hello messages all together, and each one will feel that the others are neighbors to it. Okay? So that's the first message type. The second message type is the update packets. And the update packets, these update packets or update messages, this represents the triggered updates. So if a change happens in the network, then I need to exchange an update to indicate that there is a change happened in the network. Okay? So this update then will indicate that this network is now disconnected. The cost of this network is infinity. I don't have any connection with it. Okay? I no longer have any connection with this network. So it needs to update this router and this router, because these two routers are concerned with that change. Okay? So this message update is reliable. So using RTP this message update is reliable. So this is a triggered update that happens when a network change happens, and when that network change happens, I said that this router will form a message of type update, and it will send it as a multicast to all the neighboring routers to indicate that there is a network change. And in that case, the update message is by default reliable, which means that I have to receive an acknowledgement from every single router. from all the neighboring routers. Okay? So this is what we call triggered update. So in that triggered update, I expect to have operation code, let's say 2. I don't know the exact number assigned to the update message, and this message will indicate that this network is down. If I don't receive an acknowledgement within a timeout, then I have to send the update again. Okay, so I have to wait until I receive an acknowledgement from all neighboring routers. Otherwise, I have to send the message again. That's why it's called reliable. Right? Okay. Okay. The third message is a little bit tricky now. It's called query reply. This is that's why we have 4 operation codes. We have one for hello, we have one for update, we have one for query, and one for reply. Those query and reply are 2 independent messages. For each one is actually a reliable message, which means that for query I have to wait for acknowledgement, and for reply I have to wait for acknowledgement. So this query and reply are in fact 4 messages. For query, I have to wait for acknowledgement. For reply, I have to wait for acknowledgement. So what are those used for? Well, EIGRP uses what we call a diffusion update algorithm, which tries to search for a loop-free route for a specific network. Okay? So for example, this network is down. This router will send update message to inform others that I'm no longer connected to this network. Okay, so that's done. But after that, this router still wants to send messages to this network. So maybe this network is connected through another router. Right? And this router is connected with a router that's connected to here. Okay? So it may happen that this router will send a query. It's like this router queries the network to search for a loop-free route to this network. Because it knows that it's no longer connected to it, but it's maybe indirectly connected to this network through another router. Okay? So there is a protocol called dual or diffusion update algorithm, which is used to search for a specific. This is like on-demand, creating an on-demand route for a particular network. Okay? So because we said that EIGRP uses triggered update, right? So when it starts up, it wants to, I get, for example, a packet with a destination address of 172.30.2.1. I look in the routing table, there's no such thing. I'm just starting up, right? So I don't yet have a route to this destination network, right? Because I use triggered updates, the routing table did not contain yet a route to this network. So in that case, this router will say, okay, let's keep this packet aside, send a query to the network to ask all the neighboring routers, can someone get me to this destination network or not? So that's what this query and reply are used for. So in the beginning, I need to search for a route. RIP, again, did not have to do that because RIP uses automatic updates or periodic updates. So I have to wait for the conversions to happen. Here, because it's triggered updates, okay, it may happen that at some point you search for, you try to look up in the routing table for a specific destination network and it does not exist. Okay? So in that case, you want to search for this network. Or if a network goes down and you still want to get to this network because you have removed the route from the routing table and you want to get to this network. So in that case, you send a query to all the neighboring router to ask them, do you have a route to this destination network or not? Okay. If this router has a route to this destination network, then it will send you back a reply. And as we said, query will have an acknowledgement, reply will have an acknowledgement. If this router does not have a loop-free route to this network, what it will do, it will send another query message to all its neighboring routers to ask about a loop-free route to this destination network, and so on. Okay? So this is what we call query and reply. So the query can be used as unicast or multicast, and the reply use only unicast. Of course, when you send a query, you send it as multicast, but the acknowledgement is always unicast, right? The acknowledgement is always that you acknowledge to a specific source, but the source can be from one point to multiple points. But from multiple points, each one has to send a unicast message to the source router. So the reply message is unicast. And again, both of them are reliable messages, which means that there are two acknowledgements that are not shown in this figure. For the query, there is a reply. For the query, there is a acknowledgement, and for the reply, there is acknowledgement. Any questions? Okay, so we'll talk about the dual algorithm in a little bit more details now. Okay, so quickly, the hello protocol is used to discover and establish adjacencies with the neighboring routers. And as we said, the hello protocol uses a time interval of 5 seconds, with the only exception that for multi-point non-broadcast multicast access networks, it's 60 seconds. What that is that if you have multiple routers like this, and you have a switch in between, okay? So all these routers are connected to the same switch. So this is equivalent to the fact that all these routers are connected to each other. So this is a physical star topology, but logically mesh topology, that it's all the routers are connected to each other. Okay? So this is what we call multi-point and multi-access network. Why? Because for each hello message that goes from one router, it has to go through all the other ports here, and it has to go to all the other routers. Okay? It happens for this particular topology that if you send a hello message every 5 seconds, the load on this switch will become huge. Why? Because it gets sent from this port and it gets replicated on all these ports. And every router has to do the same. Okay? So one hello message here, it goes through all the other routers. So, and another router here will go through all the other routers. Which means that you have how many messages being sent in 5 seconds? You have each router is sending to n-1 routers. So assuming that I have n routers here, so each router sends n-1 messages to all the other routers, right? So we have n-1 messages goes to all the other routers, right? And each router is doing the same, which means that these are multiplied by n. So n times n minus 1, يعني almost n square messages are sent within 5 seconds. N hello messages are sent within 5 seconds, which is a huge load on the network. And that happens because of the nature of this topology. That this forms a logical mesh topology. All routers are connected to each other. Okay? So in order to resolve this huge load, they use less frequency when it comes to this particular topology. Anyway. So for this particular topology, they use a frequency of 60 seconds to avoid sending n times n minus 1 messages in 5 seconds, which is a very short period of time. You are sending, if you have like 10 different routers, imagine that you have to send 90 different messages in 5 seconds, only as hello messages. We didn't talk about data, we didn't talk about anything. So in that case, it becomes really prohibitive. So to avoid such huge load, they use less frequency when it comes to these particular topologies. They use 60 seconds as opposed to 5 seconds. Okay? And we talked about hold time, which is usually 3 times the hello interval. So if the hello interval is 5 seconds, the hold time is 15 seconds. And the hold time is the duration that the router has to wait before declaring another router down. Now the diffusing update algorithm, which is an algorithm that's used to discover loop-free routes to a particular destination network. The advantage of using dual, again, dual is used to establish an on-demand route to a particular network. And it tries to do it in such a way that guarantees loop-free. Because remember, we talked about the fact that distant vector routing protocols, they suffer from the routing loops. So dual algorithm is used by EIGRP to guarantee that whatever route I establish, it has to be loop-free. Okay? And of course, dual provides fast conversions because it's on demand. I don't have to wait for periodic updates every 30 seconds. Here, I create the route on demand, so I can reach conversions faster than if I have to wait for 30 seconds every time to exchange route updates. So the key is that whenever any change in the network happens, router 2, again, it sends an update. We are done with this. But now I want to send a query to all the neighboring routers to ask or to search for another route for this network. The basic configuration of EIGRP again uses this autonomous system number, which actually functions as the process ID, as we said. And the important thing about that is that all the routers that use the same process ID, they can exchange messages together. If these routers have different process ID, then they are not adjacent to each other. They will not feel any messages coming from other routers if they have different process IDs. So that part we talked about. So what happens is that when you start EIGRP, you have to specify the autonomous system number. And the autonomous system number here is the process ID. So if I start this group of routers with a process ID of 1, and I start this group of routers with a process ID of 1, then these are adjacent to each other. All these exist in the same group of routers. If I use a different process ID, then all of a sudden I kind of separated those two routers from the routing perspective to two different networks. Okay? طيب. Yeah, this is very important. So the composite matrix, we talked about the fact that we calculate the composite matrix using the bandwidth and delay. Forget about reliability and load, because these are online values that we will not use a lot. What we need to worry about here is that how can we calculate the metric, assuming that K1 and K3 are 1 and the rest are 0. So we only need to calculate the bandwidth and the delay. It's very important here to realize that, well, if the composite metric here is simply K1 multiplied by the bandwidth plus K3 multiplied by the delay, which is bandwidth plus delay. So, because K1 and K3 are 1s. But bandwidth here, how do we calculate the bandwidth here? And how we calculate the delay? Because remember, it doesn't make any sense to get a summation of bandwidth and delay. Well, bandwidth is like kilohertz or something, right? And delay is seconds. How can you, So what happens is that you have to normalize these values. You have to normalize the bandwidth and you have to normalize the delay. Okay? So that's very important. When you normalize the values, you ignore the units, because when you normalize مثلا kilobits per second over a reference bandwidth using kilobits per second, so you get a ratio, and this ratio does not have a unit. Same thing for the delay. When you normalize the delay, it becomes unitless. So now you can get the summation of two unitless values. Okay, so that would have a meaning. But in normal cases, you cannot actually sum a bandwidth using kilohertz or kilobits per second with a delay which is microsecond. It doesn't work. So we need to understand how can we normalize the bandwidth, how can we normalize the delay in order to get the summation and calculate the metric. This is very, very important. Okay? So the metric calculation, the metric calculation is based on these values, is based on the bandwidth, and the bandwidth, by default, the bandwidth is 1455 kilobits per second. So this is like the default bandwidth on any link. If the link uses less bandwidth or more bandwidth, the network administrator has to manually change the bandwidth on this link. Okay, so when you start ERGRP, you have to specify that this interface has a length of, let's say, 64 kilobits per second, or 1 megabits per second, or 10 megabits per second, or 10 gigabits per second, or something like that. If you don't specify this explicitly, then ERGRP will assume this reference bandwidth of 1544, because it uses by default a T1 connection. A T1 connection is a serial T1 connection between two routers, and usually the bandwidth of this types of link is 1.4 megabits per second. Okay? But that doesn't mean that this is the only bandwidth that you can use. If your link has a different bandwidth, then you have to specify that when you set up your network. Regardless, so what we need to understand here is how. So, for example, this scenario here talks about the fact that I have the default bandwidth between R1 and R3. Okay? And I have 64 kilobits per second between R1 and R2, and I have 1024 bandwidth on R2 to R3. So only R1 to R3 uses the default bandwidth, and these links use different bandwidths, different types of links. So the question now is, if R2 wants to send a message to this destination network, how can we calculate the metric corresponding to that? This is very extremely important. As we said, we will consider only bandwidth and delay, right? So the bandwidth here is 1024 kilobits per second. And the bandwidth here, by default here, the bandwidth is 10 megabits per second. This is an Ethernet, 10 base T, 10 megabits per second. The delay of this network or this link is by default 100 millisecond. Okay, and the delay here is by default 100 microsecond. Okay, so the question now is, from this router, I want to send to this destination network. What is the metric? How can we calculate the metric in order to put it in the routing table? So the metric equals to, forget about K1 and K3 because K1 is 1, K3 is 1. Okay, so the way we normalize the bandwidth is as follows, and pay attention to this. The bandwidth, we use a reference bandwidth of 10 gigabits per second. 10 megabits per second. Gigabits per second. 10 gigabits per second, 10 gigabits per second. So we divide that by the bandwidth of the link. Okay. So now we have to pay attention to this. The bandwidth is called a bottleneck parameter. So from router 2 to this destination network, I use the minimum bandwidth across the entire path. Which means that here I have 1 megabits per second, and here I have 100 megabits per second. Which one is less? 1 megabits per second. So this is the bottleneck. It's as if you have from router 2 all the way to the destination network, you have a pipe. Okay? I need to calculate the metric based on the minimum radius of the pipe. Because this is my limitation. You want to flow some water inside this pipe. So your limit is the minimum radius of the pipe. Right? So if you have a radius of 1 megabits per second and another radius which is 100 megabits per second, which one is the limitation? The 1 megabits per second. This is the less radius. Okay? So in that case, I divide the reference bandwidth by the minimum bandwidth of any link on the entire path end to end. Pay attention to this. So the bandwidth for the entire path is 10 gigabits per second divided by 1024 kilobits per second.
So it will be given and you choose the minimum?
Yes, it will. So the 1024 will be given. The reference bandwidth is fixed. So we divide 10 to the power 7 divided by the value of the bandwidth in kilobits per second. And then we multiply that by 256. Now bandwidth is done. The delay in nature is an accumulative parameter. The delay is a cumulative parameter. The delay talks about the time that the packet takes to reach from one point to another point, right? It's different from bandwidth. Bandwidth is like the radius of the pipe. But the delay is accumulative. So the more hops you go through, the delay gets accumulated one by one. So unlike the bandwidth, the delay has to be calculated for each single hop and get the summation of all of them. So here we have two hubs. We have two networks we have to go through. This is one network, and that's the other network. So the first network has a delay of 100 milliseconds. The way we calculate the delay is as follows. The delay is the reverse of the bandwidth. So what you do is that you get 100 microsecond and you divide that by 10. Plus the other one is 100 microseconds. So 100 microsecond divided by 10. See, you get the summation of both. And then you multiply all of them by 256. Why?
What is 256?
256 is fixed value. It's like a weight. Okay? Think of it similar to K1 and K3. And it's a fixed number. You have to multiply each part of the metric by 256. So this is how I calculate the metric. This will be a big number, by the way. It will be like a huge number. So the metric here is not like 1 and 2. And it will be a big number. I will show you an example. So that's how I calculate the metric. Okay? Bandwidth is a bottleneck based on the minimum bandwidth. Delay accumulative. I have to calculate for each hop and get the summation of all. Okay? Any question? Okay. So 1 second. So these are the type of the links in terms of delay. So the fast Ethernet is the one that we talked about, uses 100 microseconds as the default delay. And for T1 connection, the delay is 20,000 microseconds or 100 microseconds. So these numbers have to be given for each link. The numbers have to be given, and it's very important to know how you calculate the metric. Bandwidth using bottleneck, delay using accumulative. Okay, so that's so we'll stop here so that we